Okay,
Yeah,
you
this is
can
okay. Yeah,
put
this
on height this little yes. Yes. Mm.
you can hide it. Yeah. Okay. So please, Salman, your master work, I think.
So here I'm have to present my master thesis research topic. Uh, I did the work I did, and what I did. Actually, I did work in a quantum optics lab there, and now I am presenting my that master's topic here in the group of laser development, which we call Gold. And my designation is lecturer, currently in Cadet College Rasmak, which is one of a prominent college in Pakistan, uh, which where we work under the army administration. So here I have to present my research work, the theoretical background and the experimental experience I get from that research. uh, my whole research actually focused on optical lensless imaging, where I used the Fresnel zone plate as a photo mask, and we used lensless techniques and different coded for that purposes. First, we construct Fresnel zone plate through MATLAB, and after that, I apply that Fresnel zone plate on the uh, SLM, special light modulator, and after that we used in the experiment. So here, what actually lensless microscopy is. First, there were imaging used were getting through. Um, like we used heavy lenses in that experiments, and that uh, uh, different imaging purposes. But after some years, we have been switched from lenses to lensless microscopy, in which we record that uh, signals and that what we call that images on a sensor, and after recording that uh, we apply MATLAB on the code we have designed in the MATLAB or Python, and by reboosting that and reconstructing that images by back propagation and different algorithms, we then highly resolve that images and work is like uh, the light microscopy, where we use heavy lenses. So, in my work, we designed a portable microscope, and which was a lensless microscope. For that, we have designed mathematical models, and after that mathematical models, we fall the light on the spatial light modulator, in which we have modulate the light, change the incoherent, simple incoherent light into structured light, and then operate it uh, and record it, and fall that light on an object, and record that object on the sensor, the CMOS sensor we usually use, and after that use phase and amplitude. We algorithm to retrieve it hidden phases and amplitude, both phase and amplitude. Um, for that, I used Fresnel zone plate, as I discussed already, and an incoherent light source. Uh, Usually, the green LED I used. Uh, and at the end, we compared final images, the conventional images, and the images from the lensless setup. So the main purpose we have, and the main challenges in that experiments we have low signal to noise ratio, uh, and twin image effect. So we were there to attain a low signal to noise ratio and to remove the twin image effect, which is the main concern in that. So both resolutions and the algorithm for the phase mm, phase reconstruction have been used, and we attained uh, improve images, better images as compared to the normal light microscope. So here we have a setup, a schematic diagram I used in my experiment. Here we apply the an illumination source, a green light LED, and falling that green LED on the polarizer to polarize this light to align in in one direction. After that, I used the mask. The mask I applied on the special light modulator. Simply we call it the SLM, and then analyze that light. After passing through these steps, the structured light then fall on the object. We used here the USAF, United States Air Force 1951 chart. Here we have different groups, and which have different elements, and the resolution of each group and element is different. So we fall that light from that transparent object, and the sensor record that objects. So do you hear me? Hello?
Yes,
Hello?
I can hear you.
Yeah, yes, I can hear you. Keep continuing.
Okay, sir. Actually, my AirPods battery got low, so that's why
Uh-huh.
I'm asking.
Mhm, mhm.
The charge component रखिएगा, तुम्हारा charger देख. हाँ. So here, can you hear me now?
Yeah, I can hear you. No problem
Okay,
this
sir.
one.
Okay, sir. So here I have the experimental setup. Actually, I used in the lab. I apply that green LED. Here is I use a polarizer, a special light modulator, which is connected to the computer device. And after that, when I apply here uh, mm,
Mhm.
uh, a mask here, which I use the mm, what I used here, and after falling that light on that mask, the structure light then fall from move toward analyzer, and then the CMOS sensor record that images, and we record that images on a computer.
Mhm.
We were connected to that sensor, and after that we apply the robust reconstructive
Okay,
algorithm.
Salman, go back a bit. I want to ask, what
Yes.
exactly this SLM, special light
SLM is
modulator? Yes.
actually, sir, it's actually a device in which we apply a structure. Usually, if we use a lens like something, or any shape, a transparent shape here, in the normal cases, if we move towards a shop and bring a shape from there, a lens from there, to fall light on that lens, and then change that light into something else, like I use the uh, mm, Fresnel zone plate.
Fresnel
So
zone plate. Okay.
like I use the Fresnel zone plate. So what the Fresnel zone plate did, like if you look here, the structure is transparent and opaque, transparent and opaque.
Mhm.
So when the light pass from these circles, the transparent, so it diffracted actually, and a
Okay.
special diffraction phenomena occur there, which structured the light, the incoming light. So
Mhm.
here we used any type of mask here. If if you desire to use a Newton rings or something like that, so you can apply make Newton rings or apply here then on the SLM and fall that light to use this SLM, the special light modulator,
Mhm.
which
Mhm.
modulate the light specially in
Mhm.
the space domain.
Okay, so it's connected to the computer.
Yes, actually, computer
So what is the purpose of connecting with the computer? Is data acquired there or controlled by computer? What exactly?
control. It is actually controlled by the computer, and compute. We apply a mask from there. It has a
Okay.
special software there with that SLM.
Mhm.
So when we install that on the computer, so
Mhm.
apply any type of mask or image there, and you can apply on this mask. So
Mhm.
the whole image, then it has a very small service. You can see here in the last lecture,
Okay, last
the
slide.
last slide.
Okay. Okay,
It
so yeah, go back to
yes.
setup. Why did you use the green? Okay, this is very small. Yeah, really. Why
Sir,
did you use the green?
I use the green. Actually, the green color is have less energy, which is very much cool color, and as compared to the blue light and or other lights, it the green light does not affect the cells here. If we use for any medical purposes, medical images, so it do not uh, did make that the cells, because
Mhm.
we at some days we bring the cells for the cancer cells from PRs, and we image their cells on this device here,
Mhm.
and
Mhm.
compared that cells numbers with the mm, other the compound microscope we took images from,
Mhm.
and compare both.
Okay, okay.
So
Mhm.
uh,
And then
so there.
CC and then CMOS sensor actually is detects, and this CMOS is how it acquires the data. It's connected to computer.
It's simply record that images, and we directly connected that sensor, CMOS sensor, with our computer or laptop
Mhm.
through HDMI,
Mhm.
and it record that images on that screen, and we then captured images and save images there. After that, we apply the code we have constructed in the MATLAB. We then put that images there by the command, and by applying the iterative algorithms there,
Mhm.
uh, it compress, and it mm, around 50 to 100 times it reiterate the images and reconstruct that images, uh, and compress that image. Like, I use the compressive algorithm,
Mhm.
and it then the twin image effect also remove there, the signal to noise ratio, it
Yeah,
also
probably.
becomes.
Salman, you go ahead because we will ask later on. This is go to the next slide, and
Okay,
probably
sir.
the that would do later. Yeah.
Okay, sir. So for my experiment, I use the Fresnel zone plate, and the Fresnel zone plate actually worked like that. I used this Fresnel zone plate to uh, to prove that this, yes, I can use Fresnel zone plate to attain the high resolution images, and to use it. So I constructed this Fresnel zone plate by using the optical instrument and its mathematical equations, Its equation is this, where the signum function is used, and I construct it from this equation by using these equation in the MATLAB.
So this Fresnel zone plate,
Mhm.
the transmission function of Fresnel zone plate, you use this equation for one
Yes, sir.
to generate.
This
Okay.
equation is actually used in the when we propagate the light,
Mhm.
and we actually when we were doing the simulation part. So in the simulation part, we actually move the LED light from here the LED toward
Mhm.
the special light modulator, and
Mhm.
there we combine that with the on the special light modulator. There is we have the Fresnel zone plate, so we use its function, the
Mhm.
transmission function of the Fresnel zone plate, and combine their transmission function of the Fresnel zone plate with the LED light, the incoherent light, and then convolve that with the point spread function, uh, one of that, and when both of these convolve, so it gives us another light, the structured light actually. So by moving that towards the objective plane, then by taking its information towards the toward the sensor plane, so the sensor plane then record that images by taking it uh, absolute square, by taking
Okay.
its intensity. So
Mhm.
then we, from these recorded intensity, we then take the phase and the uh,
Amplitude.
uh, amplitude of the light.
Mhm.
So we get the complete the detailed information from that recorded light,
Mhm.
recorded intensity, you can
But
say.
in these equations, where is the phase actually? Phase information from where do you get? In these equation, I don't see the phase.
Sir, here actually it is only the forward propagation.
Okay.
It is only the forward propagation. Here then we back propagate this light
Okay.
in the simulation, through
Uh-huh.
simulation.
Mhm.
So in that we use here these equations
Mhm.
and updated that equation to this form.
Mhm. Okay, just a minute. David is raising the hand. David was wrong.
Uh, excuse me, what is the operation of the circle with the X?
What is the operation?
Yeah,
Yes.
the cross and circle, what it shows. He's asking.
Oh, it is a convolution.
Oh,
Convolution.
Uh,
okay. Okay.
convolution.
And the dot operation below the
It is simple.
F.
Dot is simple multiplication, while
Okay.
the cross and circle is the convolution.
And the F4 and the is like the comma is like inverse operation. For
The
example, F.
comma,
It,
F prime, you mean F4 prime or
yes,
Yeah,
something like
yes,
that?
F
it's simply
prime.
F prime. It is actually a backward propagation. That's why I use here the F prime here.
Mhm.
Okay. In this case, you have, for example, in develop F3 and F prime 3. Is different in because one have the prime.
Yes, sir. Actually, here we use the F3, which is a forward propagation. The light is moving towards the sensor plane. So in while in this slide here, we move this light from the sensor plane towards this plane to attain the actual information from that, and to split each and every part. Like f4 prime is actually we took square root of the intensity. Here we recorded that intensity under root of that intensity, and then multiplied with the exponential I argument of f4, this one, this equation. We use this equation, and
Okay.
after that, by equation of f3 prime, we took the conjugate of the PSF2 point spread function to this one, this point spread function. We use its conjugate and convert it with this f4 prime. So these convolution, these actually gives us f3 prime, and then multiplied this f3 prime with the object. By this multiplication, we get the f2 prime. Clear?
Okay.
And
Okay.
after
Okay.
that, after that, the updated object, the detailed image, which have different parts. One is the O, G, plus the conjugate f2 prime divided by maximum of f2 prime, its uh, absolute square, and f3 prime minus f3. So here we get the detailed image
Mhm.
and the highly resolved image we took here
So you
to make.
subtracted the backward propagation from the forward propagation.
Yes, sir.
Mhm. Okay. Okay,
Okay.
move. Yeah.
So here there is the simulation results we took by using different R1. Actually, R1 here, it is the innermost circle radius R1, and by changing this R1, as you can see here in the transformation function and also in the resolution function of the Fresnel zone plate, that R1 is the main objective part which can change its resolution or its transmission. So here we use different R1, different innermost radius for different FZA. So by changing this R1, different images, different resolution we can see here. Like if we see is original image, original object. So by its image, if we took the value of R1 is 0.35 millimeter, means the radius of innermost circle is 0.35 millimeter, then this image, the amplitude image is this, and while taking its increasing its radius 0.5 towards 0.55 millimeter, so it's getting this, and by 0.75 millimeter its image become a more uh, clear. So if we can see here, it's the graph of that uh, PSNR, uh, signal to noise ratio, peak signal to noise ratio of R1. If we are increasing the value of R1, so its value get decreases more, and by the value of R1 it's 0.35 or something, its value get better. So here we have some experimental results, when we were using 0.35 millimeter FZA, Fresnel zone aperture, or Fresnel zone plate. So here we captured this image after applying by simple reconstruction, by applying the algorithm. So its image become this, and while when we zoom this part of the image, so we can see here that of the fifth group, if we resolve the fifth element here, which is 9.8 micrometer, so it is a little resolved here. We can see up to this group, and the sixth element, the sixth element is not fully resolved. So after that, if we match the 0.55 millimeter of using the Fresnel zone aperture of 0.55 millimeter by increasing that, so then we can easily resolve the fourth group element, which has 11 micrometer resolution, and by using 0.75 millimeter, then the third element of that fifth group is has been resolved 12.4 micrometer. At the end, we then used the multi-height by using by fixed R1, the value of R1, the FZA, but only change this height. This height means if we change the value of Z1, means moving this sensor plane and object plane, or sorry, by moving this object and the mask towards each other, then their distances has been changed from 14 towards 23 millimeter. We took images on 14, 15, 16, 17, 18 on different uh, on different planes.
Okay, but R is same. R1
But
is
R
same.
is same. R is same. The 0.55 millimeter. After that, we combine all the images through MATLAB and reconstruct to a single image. So at the end, there is the simulation part actually, and at the end, the experimental
No,
results.
the previous slide. Can you please go back? Previous slide is this is constructed, reconstructed.
Yes, sir. Reconstructed image, the simulated reconstructed image.
Simulate. Okay, it's a complete simulated, or you use the actual data.
No, sir. It's the simulation where we use the data here, like the 0.5, the value of R1 in the transmission function is 0.55 millimeter, and in the uh, like the distances here is we use in the actual experiment, we put these values in that simulation part. While then we took experimental images of the multi-height. So by taking its images at R1 0.55 millimeter, where we have fixed values of Z1 and Z2, and this image is when we were varying the value of Z1, fixed the value of Z2 while varying the value of Z1. There is at multi-height. We were capturing images at multi-height. So here, when we zoom the image, so and compare this image with this image, so here we can see that the third group is a little bit resolved, while here we have more twin image effect, and here the twin image effect has been less, but the signal to noise ratio here at the multi-height experiment is more. Means the signal to noise ratio we have at the multi-height experiment, we have the signal to noise ratio problem, but the twin image effect which is here more, but here is a little less. So that's what we did. We have developed a portable, which is a cost-effective setup of lensless imaging, and the first technique where we resolve the final image while increasing uh, mm, decreasing the value of R1, while in the second technique, the resolution has been improved, a little improved, or we can actually say that the twin image effect has been removed by using Z1 values in the sequential manner, and we can use the Fresnel zone plate to achieve the high resolution images, and our system is able to achieve high resolution of sensitive tissues without harming by using the less effective light, or by using the low intensity light, like the green light, or in some cases we also use the red light there to capture images of the
Mhm.
tissues. Actually, this image shows the special light modulator. I put that this slide at the end, because of if somebody need its information, that's why I put it at the end.
So it perform a phase modulation from approximately 0 to 1.2 pi.
Yes, sir.
What does mean?
Actually, sir, it modulate the phase of the light from 0 to 1.2 pi. If we took its values, the values of light, the phase of light, so it can change the phase if we multiply its values. So up to 1.2 pi means 1.2 multiplied by 3.14, the value we get from that. So actually up to that value we can modify its phase.
Mhm. Okay. And this code actually, MATLAB, uh, did you make this code or it was already, I mean, like,
Sir, actually, in this experiment, we were actually following a paper, a research paper, and at that we modify their code to our own use, because they were uh, performing that experiment horizontally and we performed vertically. And in their case, they were using uh, a screen to record, to show its image uh, from the screen, and the SLM and then the sensor record that screen image, while we used the LED and fall its light on the object, and then the first we fall that light on the SLM, then the object, and at the end we use the sensor to record
Mhm.
that image. So they were putting the object at the start
Mhm.
before the special light modulator, while we put that object at the end near to the sensor plane.
So what is the advantage? I mean, in this case, like you put near the sensor.
Sir, the advantage is actually that we can use, like, uh, there is different usage of the uh, this experiment in different for different purposes. Like if we use for the medical purpose, we cannot put the image, the object there at the start and display that object with a light and fall that light after the SLM, and then on the sensor plane. But
Mhm.
here in our case, we can easily put tissues or different cells, specimens near the sensor easily, and by using a slide or something like that, a sled, to fall light on that slate and record on the sensor.
Mhm. So, okay, so when you take the image, it's not a real time. You capture the image and then you apply the reconstruction.
Yes, sir. Then apply the reconstruction
Yeah,
at the
it's
end.
not a real time. It's not, you cannot see at same time.
No, sir. It's not like if you call it video capturing
Yeah.
image. Not like
Uh-huh.
that. It isn't
Mhm.
like that.
So it can be, if it is possible in this way.
Yes, sir. There a different when I was applying for PhD uh, in 2022, the university there in US, there is
Mhm.
a special group of this lensless imaging
Okay.
of a consortium of 3 to 4 universities.
Mhm.
Mm, I forgot the name of the university, but 3 to 4 universities are working on these experiments. They
Mhm.
were actually trying to capture images of the cell in the real, like by
In
using
the
the
real
video
time. Yeah.
real time.
Okay.
Here in this experiment, usually the computer department is actively involved.
Mhm.
Like in the com sets, also the computer department also work on something like that. And here in Peshawar, I hear from some people that they were trying to, like, they were using it for facial recognition.
Okay. 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 Uh-huh. Mhm. Okay. So thank you very much, Salman.
Thank you, sir.
So yeah. So David, you have a question. Please go ahead.
Uh, uh, how much this system will cost you? Do you have making a um, some information about the full cost of the system?
No, I don't have full information of it, but I think it will cost less. First, at experimental stage, it cost more. But if the industry make it, so it will be uh, cheaper than the other microscope we used in the labs, like the
Uh,
compound microscope, like other microscope.
But
Or if you compare the, like nowadays the work is also there. I discussed with Sir Taib. uh, the work is also there, started on the free X-ray electron microscope.
mhm.
So they were using this lensless setup for that purposes, to record the images of electron, and to capture images of the electron, and took information from that while using the X-rays.
Mhm. Okay.
And
Yeah. So actually,
mhm,
David, I think it will not be very expensive setup if you can make it. Like the problem is with the special light modulator. That could
yes, sir.
be. And a sensor, CMOS sensor. I mean, there are different CMOS sensors are available. It's not very expensive.
okay,
There
And
are other sensor we can also use, the
mhm,
CMOS sensor or other.
other sensors can also be used.
Yes, sir.
Yeah,
yeah,
actually,
yeah,
experimental prototype, if you make it, it will not be very, I think it will not be very costly.
Mhm.
yeah, yes. I have a talk of this topic of the lenses image 1 year ago from the
Uh-huh.
Max Planck Institute from the side of light. They have
Yeah.
Yes, sir.
a person from Berkeley University that
Hmm.
she works on it, and
Hmm.
I share you the talk, and also I share you the one experiment. The experiment they do a lensless camera with the Raspberry Pi.
Okay,
Uh,
okay. Yeah.
maybe this is
Sir,
less
Max
than
Planck,
$200. I think all the setup.
Uh-huh. Okay.
David,
You can share on
the
the
Max
group
Planck
actually.
Yeah,
actually
yes,
work on these
I
experiment
share.
also.
Yeah. Say it. Salman, say.
The Max Planck is also the Max Planck lab, or the Max Planck project. They are also using these setups, and they're working on these projects, the lensless setup actually.
Yes, probably they are working on it.
Yes.
Actually, not only there are many labs working in
Many
Europe,
labs,
actually,
sir.
In Europe.
Yes, sir.
And actually, I don't know, it can be enhanced actually. If I could get a chance, it can be enhanced. I mean, it can be modified a bit because,
Yes.
yeah, it's not very expensive setup. I mean, you can, if you have a small grant, it can be modified easily.
Yes, sir.
Yeah. So, Zanfar, do you have any question?
No, sir.
He is busy
You are
in his
missing in
honeymoon.
somewhere, I think now, Zanfar.
No, sir.
No?
There are some things which I didn't understand,
Ah,
like
you
the
something you ask? Go ahead.
yes, sir. Actually, Salman, can you move to the slide? I don't remember the slide where you show the experiment. Uh, back, back. One more. Yeah, this. I think you are showing the setup. Can you explain this to me again? I didn't understand it properly.
What, the mathematical
Not
equations?
mathematically, in general way.
Okay.
Yeah.
Actually, in this lensless setup, we have two parts of it. One is the forward propagation part, and another one is the backward propagation part. In the forward propagation part, the incoherent light, or in some cases, the coherent light has also been used. So the light
Okay.
we move towards the SLM, the mask plane, and at the mask plane, we used any type of mask. Like here, we use the Fresnel zone plate or the Fresnel zone aperture, and so we use the equation of that Fresnel zone. Okay, then we here the incoherent light and the transmission, its transmission function multiplied, they combine. Then the point spread function of it convolved with that.
Actually, you are multiplying because of uh,
Mhm.
for the modulation. You are multiplying these
What?
two coherent and incoherent light.
We are multiplying what? The incoherent light and the mask we applied here. In our case, the Fresnel zone plate. We are multiplying these both. Due to multiplication, only simply they multiply. But through convolution, the whole information multiplied there. Actually, this PSF1, the point spread function, this actually hold the whole information of the light it have. Okay,
Okay. Okay.
so after that, this convol term, the f2 function, and the object, when we light move towards the objective plane, so by passing light from that, they both multiply and then convert with the point spread function f2. Okay, so these when multiply, when convolved, they took the whole information, and the f4 function comes there, in which we have the PSF2 multiplied by f3, actually hold word the PSF1, which is convolved with the f1, which is TRP LED and the object. So the whole information combined there in the f4. Then we record that f4 at the sensor plane by record its intensity. Okay.
Okay.
Mhm.
In the backward propagation model, we back propagate from this sensor plane
Hmm.
towards the object plane
Object
and
plane.
then at the
Hmm.
mass.
Hmm.
At that, we took under root of the intensity and the exponential function, this one, and then convert that by taking its conjugate, and then we using different Fourier optics terminologies and equation of the Fourier optics, and then at the end we update in this form.
Okay.
Okay.
So what's the benefit of the forward and backward propagation?
The forward propagation, actually light moves in the actual form in the forward direction, but the backward propagation, in the backward propagation, we split each and every term in its own way, and we apply the algorithm there by using this equation. We apply that compressive sensing, the iterative algorithm there in the MATLAB, and this image then highly resolved, and each part is clearly visible in the image then as compared to the normal image. Actually, we recorded this image.
Okay, means you want to say in simple words to increase the resolution we use the forward and backward propagation.
Sorry, your voice has been interrupted.
I am
Sorry, sir,
saying
repeat your message.
for the highly resolution we do the forward and backward propagation.
Forward is the actual way of propagation of light. It actually the light actually propagate in the forward direction, as we know from our experiments or daily life, that we record what our eyes record is the actual intensity. This one, what other cameras record is this. But what we were doing there is the backward propagation. So the whole story lies here in the backward propagation model.
No, but Zanfar is asking, why do you need the backward propagation?
To resolve, to highly resolve the
Yes,
recorded
this is what
image.
he said. To resolve.
So that is what I'm constantly telling
Mhm.
him and explaining him, that
Mhm.
uh, the normal cameras, the eye or any sensor is using to record this thing.
Mhm. Mhm. Yeah.
But what we do in the lensless setup or in the high resolution setup, we did this.
Mhm.
Okay,
Okay.
okay.
Okay. So,
So,
now
sir, one more
one more.
question.
Okay. Okay. Go ahead. Go ahead.
Uh, uh, can you move to the sound signal noise ratio graph? Yes, this one. Uh, can you explain this? What this graph is showing?
This graph actually shows that as we increase the value of R1, so the value of the signal to noise ratio is getting decreased. Here, this is the
Means
Y part,
we are getting signal resolution, high resolution.
signal to
No,
noise
that is
ratio.
noise ratio. That is signal to noise ratio.
Okay.
Okay.
So it's a decrease
So
when R is increased.
as we increase the uh, inner radius, the innermost radius of the FZA, so the peak signal to noise ratio getting decreased.
Mhm.
And
Okay.
limit and its limit is up to 0.7, or we can say that 0.8. After increasing its radius more, so its value get decrease. Its value then disturb the signal to noise ratio, or the high resolution value. Its value become then